Welcome to the 16th session on measure theory. This is the fourth session on measurable function and second session on sequences of measurable functions. In the last session, I wrote wrongly. It must have been measure 15 and measurable functions 3. I wrote it wrongly. That doesn't matter, but at least measure and the video's numbering is very correct, thanks to Professor Baba Sharma. he, he is very, very meticulous. He is keeping track of such things. Okay, so today I want to talk about only two results. Okay, one is something to the sequences. Yesterday we saw, in the last session, we saw that UFN is a sequence of measurable functions, and if it converges to a function f point-wise, then f is measurable. We also saw in the case of a complete measure space, in particular with respect to the Lebesgue measure, if f1 converges to f almost everywhere point-wise and f1s are measurable, then f is also measurable. Okay, the convergence need not be at each and every point. Okay, f1 of x converges to f of x for almost all x. Okay. Now I already gave yesterday one applications where it was actually point-wise convergence. If f is a differential function, then the derivative f dash is measurable. It need not be continuous, but it is measurable. The way we proved that was, we proved there exists a sequence of measurable functions which converge to f dash point-wise. Okay. Now today's thing, I told you I kept us a suspense. Today's thing is we want to use that almost everywhere convergence. So again, to put everything in perspective, it's always good to know, never ever learn things just because of theorem proof. Okay. Learn with context. Remember, when we define almost everywhere concept, we distinguish two things. I have a function f from R to R, and I said f equals to g almost everywhere where g is a continuous function. Then f is measurable. Right? That is, f is some function equal to g, a continuous function, but not at each and every point, almost everywhere. Then we proved f is measurable. Okay. That is because whenever f is a measurable function, f equal to g almost everywhere in a complete measure space, then g is automatically measurable. That's the part we used. But there is a second one we designed. If the notion of a function being continuous almost everywhere, that is the set of points of discontinuity is of measure 0. Then the question is it measurable? Okay. And most often this is not proved. Okay. In fact, to be very frank, just a week ago, I know the proof, but the proof involved too many things. Later we are going to show that any Riemann integral function is going to be measurable. Okay, using that only I can prove that. And there is also Lebesgue criterion. A function f is Riemann integrable if and only the set of points of discontinuity is of measure 0. That is Lebesgue theorem. Using this only I could see a proof. But today we are going to discuss a proof which is straightforward, simple, and also it gives a very beautiful application of the result. If f1 converges to f almost everywhere, f1s are measurable, and then f is also measurable. We are going to make use of this result. I hope you enjoy this. It's very likely it will never ever be asked in exams, but in this exam, the proof will involve a lot of interesting things, ideas, very simple ideas. Okay, I will explain after the proof again. It's a lot of preamble, right? I hope. Are you intrigued? I hope so. Let us get started. So, this is the thing we want to prove. F from R to R, this is application 2. R is continuous almost everywhere. That is, there exists a set D, okay, so that X in R, so that F is not continuous at X. So these are points of set of points of discontinuity, then measure is 0. So if X is not in D, then F is continuous at X. Okay, right. What we want to prove is F is measurable. Okay, and I will go through the proof line by line carefully. Okay, yeah, I'll go through the proof line by line carefully. Then, if there is time, if you are interested, I will explain how one thought of such a proof. Okay, so what we want to do is, let us look at R. Okay, this R is union of K plus 1 semi-interval K in Z. This again, okay, you take it for granted, but this in my book and also in my lectures, videos on real analysis, this is a fallout of greatest integer function. What does it say? Given any x, there exists a unique K, an integer, okay, this is unique, so that K is less than or equal to x, strictly less than K plus 1, right? So the basic idea is, therefore, give me any x, it has to be in one of them, K to K plus 1. Okay, there is a unique K. Okay, right. Now, for each n, what I want to do is, this one, I want to divide into n parts again. That, okay, each one of them will be 1 by n size. And what will be the point? This will be kn by n, then k plus 1 by n, and this will be k plus n by n. Okay, these are the nodes, right? K plus 1 times n by n. Sorry, k by n, and next will be kn by n plus 1 by n, therefore kn plus 1 by n. And this will be kn plus n by n. Okay, is that clear? K, write it as kn by n. The next point will be 1 by n, that is kn by n plus 1 by n, that is kn plus 1 by n. And the last one will be k plus 1, that I am going to write kn plus n by n. Is that okay? So each of these nodes is length 1 by n, right? Therefore, for each n, R is again a disjoint union of intervals of this kind, k by n, k plus 1 by n, as n varies over z. Sorry, k varies over z. Okay, you understand that your actual k will be something like, if you are looking for m plus 1, that interval will come as k equal to mk. That's what we found out. Okay, pause, review, proceed. So this is a disjoint union, right? Therefore, given any x in R, there exists a unique and fixed n. Okay, there is a unique k in Z, such that x belongs to k by n and k plus 1 by n. Is that clear? Okay, right. Now what I want to do is, I want to construct a function fn. These are what you call, if you have learned Riemann integration and also my first three lectures on measure theory, intuitive ideas, intuitive geometric ideas, I would have introduced what is called step functions, right? Those are the functions where the function is the constant on this and multiplied by characteristic function. Okay, they are the form f equal to summation ci into indicator function of ji, where ji's are intervals. Okay, so I want to construct such a thing. So f1 I want to construct as f of k by n into indicator function of k by n, k plus 1 by n. So notice that I have r, I have k by n, and this will be k plus 1 by n, and the value here is going to be the value at this point, the left hand end point. Okay, my fn of x for each x here will be f of k by n. Do you understand this? So this is, let me write legibly, f of k by n into indicator function of k by n, k plus 1 by n, where this k varies over z. Okay, please understand this. So spend some time. Okay, right. The next thing is why is f1 measurable? Okay, that's the next thing. Now again there are two ways. Notice that each one of these fellows, f k by n, indicator function of k by k plus 1 by n. Okay, this is a scalar multiplier of characteristic function of a measurable set, because each one of them is a measurable set, and you have seen indicator function of E is a measurable function if and only if E is a measurable set, right? Therefore each one of them is a measurable function, right? And you are going to have sum, right? This f1 itself, you can think of this, okay, is a limit of s n m, where s n m is minus m2 plus m of f of k by n at indicator function of k by n to k plus 1 by n. Okay, and yeah, these are finite sum, these are all measurable, and there's a limit, therefore it's measurable. Okay, but I give a different proof. Okay, this okay, this is fine, but we will find another proof. So let us go back to the definition. Give me any alpha in R, I have to show f1 greater than alpha is a measurable set, right? Then to show fn is measurable, it's enough if I show this. Okay, right? Now let's look at, start with any x in R. So let us look at set, let x belong to fn greater than alpha. What does that mean? Fn of x is greater than alpha. But what is fn of x? There exists a unique k in z such that x is belong to k by n, k plus 1 by n. Therefore f of x, fn of x is f of k by n. That's what we observed earlier, right? Therefore this is okay. So what we want is this must be greater than alpha, right? That means given alpha, okay, look at the set of k in z such that f of k by n is greater than alpha. Okay, then therefore fn greater than alpha. When does it happen? This happen if, okay, therefore this x belong to this if and only if there is a k such that x belong to k by n, k plus 1 by n, and f of k by n is greater than alpha, right? Therefore, this set is union of such k by n. Not all, only those k. So that f of k by n is greater than alpha. And each one of them is measurable. This is a countable union. Therefore, this is measurable. Hence, we conclude Fn is measurable. Pause, review, proceed. Okay. Why did I think of this proof? There are two reasons. Okay. The first one is, as I keep saying, it's good to learn mathematics just for the sake of understanding and enjoying rather than for exam purpose. One of the standard exercises for a continuous function on a closed and bounded interval AB is that there is a sequence of step functions which converge to F uniformly. Let me repeat. If F is continuous from the closed and bounded interval AB to R, then there exists a sequence of step functions Sn, okay, so that Sn converges to F uniformly. This follows from the uniform continuity. This would have been done in my book on real analysis and also in sequences of uniform convergence when we discuss about uniform convergence. Again, when we talked about Riemann integration. Okay. The second reason is, as I said in the start of the lecture, it's a well known that a function, Riemann integral function, is measurable. The way you prove that is using two results. One is that, okay, the one, and second one is there is a Lebesgue theorem one which says the points of discontinuity of a Riemann integral function is of measure 0. It's an if and only if condition. Okay. And the proof that any Riemann integral function is Lebesgue integral, which I'm going to see after about 10 or 15 lectures, 10 lectures at least, uses step functions. Okay, step functions coming out of either lower Darboux sums or upper Darboux sums. Okay, and it's like a converges point almost everywhere to F. That's the reason we will be using it. Okay, but please ignore. It assumes a lot of things. I am just excited to say how one thought of such a proof. Okay, so because of these things, this proof. Okay, the sequence F1 is constructed. So these few minutes you can simply ignore, and later when you are confident you come back and see that. Okay, so let's go back. So we have shown F1 is measurable. The next thing we want to show is let x not in D. Remember, D is a set of points of discontinuity. Okay, x is not there, therefore f is continuous. Then I want to say F1 of x converges to fx. Okay, for all x, that means F1 converges to F point-wise almost everywhere. Right? Then we know these are measurable, and this is a limit of point-wise convergence almost everywhere. Therefore, by our limit theorem, we know this is measurable. So we have proved the result. Is that clear? So what needs to be shown is this. If I show that, the proof is complete. Now let's look at this. Okay. If I look at x, okay, for every n, there is a unique kn. Let me only call it as k, an integer, so that my x belong to k by n, k plus 1 by n. Right? Therefore, this is my k by n. This is my k plus 1 by n. The total length is 1 by n, and my x has to be somewhere here. Okay, it may be anywhere, right? Therefore, the distance between my x and this k by n, call it for example tk, okay, tk equal to or tn equal to this particular k by n, yeah, and this tn is less than 1 by n. So what is tn? This is the left-hand endpoint. This tn is nothing else than the left-hand endpoint of this unique subinterval to which x belongs to, right? Therefore, my tn converges to x, right? But since f is continuous at x, okay, this is tn, not fn, okay, right? F of tn must converge to f of x. But what is f of tn? It is f of k by n. That is by definition fn of x. Therefore, I have proved fn of x converges to fx. Therefore, my sequence fn, these are all measurable, and fn of x converges to fx at x points of continuity, and this is almost everywhere. Therefore, fn converges to f almost everywhere, and hence f is measurable. Okay, so go through the proof, pause, review, proceed. Please go through the proof from the beginning. Some of the ideas how I thought of such proof you can simply ignore. Just plain go through the proof. Okay, we did a lot of interesting things to prove fn's are measurable. Okay, how to look at such things. Okay, and we also showed that fn converges to f almost everywhere, and you will be one of the very few who have seen a rigorous proof of this result. Okay, later people only kind of try to bulldoze you with a lot of more difficult results, and from that they will conclude, whereas we have a simple direct proof. Yeah, I hope you enjoy it, learn it well, discuss with your friends. Okay, so the next thing we want to do is something nothing to do with the sequence of measurable functions. I should have done it before starting sequence of measurable functions, but I didn't do that. So what I will do is I will do it now. It's some kind of isolated result. Again, if you don't want, you can ignore that, because again I am going to do a lot of insights. Okay, I am going to compare with some results in topology also. Okay, you will enjoy. If you enjoy mathematics, you will enjoy this. Otherwise, ignore it. If you are worried only about understanding measure theory for exam purpose, then you can ignore what is going to follow now. So let us look at our definition of measurability. We said f from, we are only in R, okay, x at b to R. Let us keep only R, don't worry about extended, okay, measurable. Our first definition said for every open interval, if you want, J, f inverse of J must be measurable. And of course we saw it's equivalent to for each alpha in R, this is measurable. Okay, if you know topology, I can say something more, but let's not worry about it at present. Is this clear? Now what I want to say is if B is an R, is a Borel set. What is that? Remember, script B is the Borel sigma algebra. What is this? This is the smallest sigma algebra containing all open sets. All open intervals and hence open sets. Right? Okay, so I want to show if B is a Borel set and if F is a measurable function. So this is, let me say this is B of R. Okay, whenever Borel set, it's a all. Okay, it's better to do that because general sigma algebra also I am unfortunately denoted by B. Maybe I should have chosen this, but then this will be like a summation. Sigma algebra for sigma. Anyway, okay, to R. Suppose this is measurable. Then I want to claim for every B in Borel sigma algebra, that is every Borel set F inverse of B belong to B is measurable. Okay, understand this result. So not only inverse image on an open set must be measurable, inverse of image of any Borel set also should be measurable. Okay, notice that Borel sigma algebra is simply the smallest sigma algebra containing all open sets. You do not have any kind of complete description. You give me a set B in R, I do not know how to prove it is a Borel set. Yeah. So how am I going to prove this? So there is no description. For example, if we say G dot Z or F sigma Z, I know what they are. Okay, this is going to be intersection of open sets, and this is going to be union of closed sets, and etc. etc. So I can use inverse images easily. But here I do not know. Okay, the trick is the following: let A be the set of subsets B subset of R, so that F inverse of B is measurable. That means this will belong to B, the sigma algebra on X. Right? So what I know is all open intervals, if J an open interval, then J belong to A. Is that clear? Now if I show, if we show that A is a sigma algebra, then B of R is the smallest sigma algebra which contains all open intervals. It has to be contained in A. That means for every B in BR, F inverse of B will be measurable. Do you see that? This is one of the very standard way of dealing with sigma algebra in measure theory. That's why I wanted to give this proof. Is this clear? So to show that this is a sigma algebra is very easy. Let us look at. The first thing is empty set belong to A. That is very clear. Right? Okay. Or R itself you take. Okay, that belongs to A, because R is union of intervals, open intervals n and Z. Therefore F inverse of R is going to be union of F inverse of minus n. Okay, and these are all in B. It's a countable union. Therefore this is also in B. Therefore we have proved the first condition. The second condition is, if B belongs to A, I have to prove B complement belongs to A. Right? But that's very easy. Again, it's involves foundation course material. That is, what is F inverse of BC? F inverse of BC is nothing other than F inverse of B and its complement. Accept it for a minute, then this is clear. Since B belongs to A, F inverse of B belongs to script B, the sigma algebra on X, and this is a sigma algebra, therefore the complement also belongs to this. Therefore this F inverse of B belongs to this. That means BC belongs to A. Yeah? Pause, review, proceed. The proof of this is very easy. Okay? I do not know that I should spend time. If you are a good student, you may get irritated, but skip it. Okay? So if X belongs to the left side, F inverse of BC, if only if Fx belongs to BC. If only if BC. If only if Fx does not belong to B. This is if only if X belongs to F does not belong to F inverse of B. That is if only if X belongs to F inverse of B complement. Okay? I hope I did it correctly. Okay? So we proved this result. Is that okay? The third thing is, if suppose Bn all belong to script A, that means F inverse of Bn or each n in n, they are in the sigma 0 on A, then I want to show union Bn script A. That is again easy because of inverse images behave well with respect to this. F inverse of union Bn or n, this is nothing other than union of F inverse of Bn. And each one of them belong to B, it's a countable union, right? Therefore this belong to B. Okay? Right, now why is this true? The proof is again easy. If X belong to F inverse of union Bn, if you had watched my foundation lectures or if you have seen my topology lectures, all these things are already proved. Okay? Very rarely in the courses, either in BSc or master's degree, teachers teach these things. Okay, this if only if Fx belong to union Bn. This is if only if there exists n, so that Fx belong to Fn. This is if only if there exists n, so that X belong to F inverse of Bn. This is a if only if X belong to union F inverse of Bn. So we proved the result. So let's go back. Therefore, our script A was set of subsets of R so that F inverse of B is measurable. Okay. Then we proved this contains all open intervals and hence open sets, and it's a sigma algebra. And therefore, Borel sigma algebra, which is the smallest sigma algebra, okay, is contained in script A. That means for every B Borel set, F inverse of B, F inverse of B is measurable. The converse is obvious. Okay. So conclusion, F from X B to R is measurable if and only if for every Borel set B in R, F inverse B is measurable. So we proved this way. The converse is easy because you start with any open interval, all right? Then it's a Borel set, therefore F inverse of B will be measurable. Therefore this is easy. This we proved. Okay. All right. One of the standard principles we should learn well is inverse images. Okay. There's inverse image under some functions. They behave well. Okay. Now, they behave well with respect to union, complementation, intersection, etc. And arbitrary union. That's also very important. Okay. In fact, I just cannot resist myself from saying this. What I am going to say has nothing to do with measure theory. Okay. And it has something to do with points of topology. If I learn quotient spaces, or if I learn unified view of subspace, product, and quotient topologies, one of my lectures in topology playlist, you would have seen this. Okay. Okay, I'll just give a thing so that you should have some kind of a global picture of mathematics, not only localized. Okay, theorem proof. Okay, right. See, the problem is, suppose I have a set, this is a topological space, and I have a set y, and suppose I have a function f from x onto y. Think of this onto, okay? A typical case is, if I have an equivalence relation on x, my y is the set of equivalence classes. Right? Now I want the largest topology. call it tau f on y, so that f from x tau to y tau f is continuous. The way we do that is very simple. You start with a v in y, then we declare or we demand or define, okay, v belong to tau f if and only if, that is so open if and only if f inverse of v belong to tau, that is open here, right? And then using the earlier results as above, you can see this collection, that is this collection v is a subset of y, and so that f inverse of v belong to tau is a topology on y. Not only that, it is the largest topology. If I suppose I have a tau dash, a topology on y, so that f from x tau to y tau dash is continuous, then tau dash is contained in tau f. That is because you start with v in tau dash, then f inverse of v is in tau. By definition, my v belong to tau f, right? I went through a little fast. I just wanted to give you a taste of some things and kind of what you call, make you curious. Yeah, please check with my topology lectures on unified view of subspace, product and quotient topology, or you can look at my article which you can download from the expository article site, or from my topology book, of course. The topology book is joint author by Vikram Maital and myself. Okay, please go through that. And remember, both the things today taught a lot of things about measurable sets and measurable functions, and the notion of almost everywhere convergence is the first part. Okay, please learn that well. Okay, we'll meet again.